This weight has a 10 on it. That means it weighs exactly 10 pounds. Or does it? Hello and welcome back to the Fundamentals with Hathy. Today we're going to be talking about weight and mass. Weights are calibrated for standard gravity, which is the average acceleration at sea level in 45 degrees latitude. That's exactly 9.80665 meters per second squared, or this in feet per second squared. But I'm in Boulder, Colorado, which is not only at a lower latitude of about 40 degrees, but also about a mile above sea level. That means that the gravity out here is actually weaker than standard gravity. In fact, it's 9.798 meters per second squared. That's a difference of 0.088%. Well, that isn't a huge difference. This does mean that the 10 on this weight is technically wrong. The weight's actually about 9.9912 pounds. But that's only if we stay right here. If we send that weight anywhere else in the world, that number will change again. If we want a constant number, we'll have to use mass. Mass is essentially a description of how much stuff is in an object. It doesn't vary with gravity, it just describes how hard something is to accelerate. Imagine throwing a ball filled with air and one filled with rocks. It's harder to get going because it has more stuff in it. Mass and weight are related, but while mass is some nebulous resistance to change, weight is actually a measurable force. To find an object's weight, you can multiply its mass by local gravity, or you can measure its weight and then run the equation backwards to find its mass. It's also worth noting that pounds is specifically a unit of force or weight, while kilograms is a measure of mass. If you want to measure forces in metric, you should use newtons, and if you want mass in imperial, you should use slugs. So let's describe this weight in kilograms so it's not constantly changing. Okay, sorry, I didn't have a kilogram weight, but this will just have to do. No matter where we take that weight, even space, it will always have a mass of 4.53592 kilograms. Which means you would actually be able to lift 3 times as many kilograms on Mars while lifting the exact same number of pounds. This results in an interesting quirk for scales. If this scale is in pounds, it's right. But if I switch it to kilograms, stone, who uses stone? Kilograms, then it's wrong. When I move it up and down, the number for kilograms changes, even though the mass is staying the same. But when it's in pounds, it's just accurately reporting the force. Now it's time to acknowledge the 2 elephants in the room. Pounds of mass and kilograms of force. Metric guys, I'm looking at you. One of the reasons we love metric so much is that it makes conversions easy. 1,000 meters is a kilometer, 1,000 grams is a kilogram, 3,600 seconds is an hour. I'll have to let that one slide. But then you guys had to mess it all up. A kilogram of force is 9.80665 newtons. Imperial's no better, a pound of mass is 0.031081 slugs. Ugh. So what's going on here? Basically, someone wanted to be able to swap between mass and force without doing any math, so they made up a new unit, which meant that 1 kilogram would create 1 kilogram of force. Or, for Imperial, 1 pound would be created by 1 pound of mass. This is stupid. But that's only at 40 degrees latitude and exactly sea level. Anywhere else in the world or anywhere else in the universe, this just doesn't work. So, all you people who think you're more scientific when you're using metric, maybe think twice before saying kilograms of force because it's a disgrace to the entire metric system. Well, that and the fact that there's 365.2422 days in a year, but that one can't be helped. Imperial's no better, a pound of mass is 0.03181 slugs. That's wrong. That number is wrong. One of the reasons we love metric is that it makes conversions easy. 1,000 grams is a kilogram, 1,000 meters is a kilometer, 3,600 seconds is an hour. I'll have to let that one slide.